So Monday, we did this problem. The integral over the quarter circle in the first quadrant of x, y, ds. And I said, this is the height of a fence. And I kind of drew it in the air with my hands. Well, here, there's my quarter circle, right? There's the quarter circle raised xy, and there's the area under it. So if you want to know what a line integral looks like, this is it. This is the one we did in class. And the area under here was what we calculated to be pi over 2. So I brought it. But today is question and answer day. So vector fields and line integrals. What questions do you have?
Question 6 and
Question 6. So we can do this in 2 different ways. We can draw it by hand, we can draw it on the computer. Okay, so if I'm going to draw it on the computer, I need to open up Grapher. 6. 6 is a 2-dimensional vector field. So I'm going to leave it in 2D mode. Now let me share that to the recording so you can go back and look at it again later. Okay. So what we're really creating is a vector field that is a slope field. So it's not going to be necessarily long enough or short enough, depending on the way we draw this in. I'm not going to do 6. Do you want to do 5? Or why don't we do 5? Because it looks very similar to 6, okay? So 5, I need to go back to my video for a second so I can actually write this thing out properly. Number 5 says that my vector field is yi plus xj over square root of x squared plus y squared. Now what I'm going to do is I'm going to break that into 2 pieces. I'm going to write that as y over square root of x squared plus y squared, comma, x over square root of x squared plus y squared. So now instead of writing it in I and j, I've written it in components. With me so far? Okay. So what I'm going to tell it to draw is a slope at the point xy given by that equation. So let me go type it in. In Grapher, I need to move this thing out of my way. There's where all of my things are hidden, in that little sigma over there in the corner. So get rid of this. I need that capital delta. I type that out as the word D-E-L-T-A. As soon as I hit the A, it turns into a triangle. And then I need that matrix set up. So that vector, 2-dimensional equation. It's just xy. I lost the delta. Let me go put that back. There. Equals. Now I need another one. And now I got to put in the pieces. So in that top piece where the x is, click on that x and replace it with y over, square roots are under the thing. So square root there, x to the second plus y to the second. Go down here, replace the y with x over, again, find the square root, x to the second, drop plus y to the second. I was up in the exponent. I had to hit the right arrow to get out of the exponent. Now, as far as I'm concerned, you can print that. I'm perfectly happy with that.
So Why do you have the y as the value on top for the x and the x and the y?
Because back here, I and J,
Oh,
I and J.
so that says.
I'm doing this in the X direction, I'm doing this in the Y direction. This is in the X direction, this is in the Y direction. This is with both of them. That's why it ends up with both of them. It's X times the vector I, it's Y times the vector J, right? So another way I could write this vector field is to write Y over square root of X squared plus Y squared I plus X over square root of X squared plus Y squared J. And this would be like the P and the Q functions. Which is the same as writing like that. So that's the whole idea. Is I take the I part, put in the first coordinate, J part. If it was in 3D, I'd put the K, the R in the K component. Yay! And then take your picture, print it out, write what number it is. I'm perfectly happy. If the arrows come out looking differently, we can hit the inspector button up here. First, I make sure that's selected. I hit the inspector button. Notice what's unchecked, bottom of this box. There's that arrow, that little box that says proportional. So that's why all my arrows are the same size. If the arrows come out different sizes, you've got that box selected. If they come out in rainbow colors, then you've got to use colors there. You can turn that off, make them whatever color you want. I had just selected one thing. But if I turn on proportional, you'll see that the closer we are to 0, oh no, these are normalized. Because they've divided by length of x squared plus y squared, aren't they? These are all the same anyway. Ooh, I didn't notice.
The magnitude is the same.
Right, because it's y over x squared plus. What's the length of that? The length of that vector is 1 every time. So all of those vectors were the same size, and I just didn't notice. I'm going to be the first person to tell you I hate drawing these pictures. But there's something in this vector field that to me is kind of important. And I can really show it in the picture. In the picture for this vector field, you'll notice there's a flow to this vector field, right? In this direction, all the vectors are coming in. But notice if I were to draw the line, y equals minus x, even up there in the second quadrant, they're coming in that direction. And along the line y equals x, they're going out. So really, in effect here, there's a flow going on, right? And we should be going this way. If I were to think of something in this vector field, like a particle, right? Moving according to these arrows, I could draw out the path it would move on. Those are the paths that I want to integrate on when I do line integrals. And normally I would want to know, hey, what's going to happen in the long term? And in the long term, in this case, things are going to end up going this way. Because I've got a line that tells me which way we go in the long term. If I were to try and figure out an equation for the curve described by a particle moving in this vector field, I'd have a solution to the equation that says my derivative is this thing. And I started at this point. That's a differential equation. Guess what we're doing next semester in PQ? But that's exactly what we did in chapter 9 last semester in Calc 2, where we solved differential equations, we were just doing it in one variable, not two. I can do all of this stuff. More questions on the picture?
You said we could just print.
Yeah, absolutely. Screenshot it, print it out, print it right from here. I'm not sure how to print from Grapher off the top of my head. And yeah, just put the number on it. I'm good. No, I don't. I want you to draw all of this by hand and take an hour and a half to do. No. More questions?
Seem to get a picture for when it's just X, Y, the one on X, Y, Z. Maybe be my graph, but I feel like it gives me trouble sometimes.
Sit down with me right at the end of class. I'll look through specifically your tech pieces, because if it's your tech, we'll have to do something about Grapher and we'll have to fix that. Because hey, you've got to make sure you're in the right setting, right? So if you're here, it says this is in a 2D picture. If you're in a 3D picture, you can't graph just in 2D. So when you actually say, so file, new, it'll ask you, do you want a 2D or a 3D? If you're in 2D, you can't graph 3D. And if you're in 3D, you can't graph 2D. It's an easy tech mistake. More questions?
Mm-hmm.
20. Evaluate f.dr where the curve is and the function r. Okay, so let me start with 20. Let's do 21 because it's also 3D. Okay. So 21 says that your function f is sine x times I plus cosine y times j plus xz times k. So then here's p of xyz, q of xyz, and r of xyz. And r itself is t cubed minus t squared plus t cubed I minus t squared j plus tk. It also gives me a range for t. It says 0 less than t less than equal to 1. So far, so good? Okay. Best part about this. I'm going to turn the entire thing into an integral in t. dr. dr means take the derivative of r. So as a vector, r is t cubed minus t squared t. Yes? So what's the derivative of that? dt. Right? That would be dr dt. I just moved the dt to the other side. F. F is in terms of x and y and z, right? Not anymore. I'm going to take the x and y and z that are here and put them in to f. So f sine x cosine y xz becomes sine of x sine t cubed, cosine of y cosine minus t squared, and then x times z t to the fourth. Nope. Now I'm doing this integral, right? integral over C f dot dr is now going to become an integral in t. Here's the vector for f, sine t cubed, cosine minus t squared, t to the fourth, dot dr. 3t squared minus 2t1 dt. Do the dot product. Oh, so I take the x component here times the x component here. Sine of t cubed times 3t squared plus the y component times the y component. Cosine negative t squared times negative 2t plus t to the fourth times 1 dt. Best part. There's a u sub here. There's a u sub here. These integrals are now all easy. Now, what does this represent? This line integral is work. The work done by this force on a particle moving along that path R in three-dimensional space. I don't know what this vector field is doing, because literally I have no idea what this picture looks like, but I could graph that vector field, and I could graph this curve in that vector field. And then I could see, oh, we're going from here to here, and the vector field is pushing in this direction. How much work does it do as we move? So I'm going to get sine of 1 minus sine of 0 plus cosine of 1, negative 1 minus cosine of 0. And then t to the fifth over 5, 1/5 minus 0. Antiderivative sine. Antiderivative sine, cosine. Result, some ugly decimal. More questions? Yes. Number 8.
Yes.
So this is where we have to do two separate curves, right? So I've got an integral. Part of a circle and then part of a line segment. So let me actually just start with the curve. The part of the arc of the circle x squared plus y squared from 2, 0 to 0, 2. From 2, 0 to 0, 2. And then from 0, 2 to 4, 3. Okay, hang on a second. I'm really happy to see that we're going this way around the circle. What are the parametric equations for my circle? And what's your range of t? Beautiful. Then that's going to be curve 1. Now I need curve 2, the line segment. This is the one where I have a formula written down. A line segment is 1 minus t times the starting point plus t times the ending point, 0 less than or equal to t less than or equal to 1. Every time. So C2 where did we start?
Two or 0, 2.
And we end at? So that's something times 0 plus 4t, and then 2 times 1 minus t plus 3t. And if I multiply that out, 4t, 2 minus 2 plus 3 plus t. Now, if you wanted to, you could write x equals 4t, y equals 2 plus t. And now you have parametric equations for the first integral, part of your integral, and parametric equations for the second part. I'm going to do the same thing we just did in the other integral, right? We're going to do the integral x squared dx plus y squared dy, right?
That's what you just. The x and dy.
Yep. But I first have to break this integral into the integral over C1 and the integral over C2. So here, I'll use the circle pieces for x and y and dx and dy. And here, I'll use the straight line pieces for x and y and dx and dy. One of the integrals goes from 0 to pi over 2. The other integral goes from 0 to 1. Sure. Which one? Pick one. Okay. So in the second one, it's the integral from 0 to 1, x squared dx plus y squared dy. Derivative of 2 plus t is just 1. The derivative of 4t is 4. The other one's going to be a bunch of trig stuff, right? Yeah, you're still looking at this board like it hit you with a fish. Talk to me. With this sort of shell shock look on it. It's okay. It's that kind of day, I understand. More questions? I don't know, maybe you're still studying for that med exam. You were talking with Maddie yesterday. No. Integral xy to the fourth, and we're doing the right half of the circle. Okay. That dx, dx, dy, that is, wait. X squared plus y squared equals 16. Okay, wait a minute. Right half of a circle. I'm slightly irked they didn't give me an orientation. They didn't tell me whether I'm going up or down. I'm going to make it the easy way, and I'm going to assume I'm going to go on the right half. To make my life easier, I'm going to go that way. But wait a minute. What's the radius of this circle? So x equals y equals, and a boundary for t. You get parametric description of this circle. Bing, 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 bing. Now, what are the bounds on t? I start down here, and I go to there. Wait a minute, what angle's that? Ready for the better part? DS. I need x prime squared. Derivative of 4 cosine t. Oh, the derivative of cosine though is -4 sine t, but that gets squared. Derivative of 4 sine t. But that also gets squared. And when you square this, you get 16 sine squared t plus 16 cosine squared t, which gives me yay! Ready for the fun part? X, Y, ds. Let's do it all in t. Integral of x, y to the 4th ds over this curve is the integral of minus pi over 2 to pi over 2. X is 4 cosine t. Y is 4 sine t, but that's raised to the 4th. ds is 4 dt. Except for the giant number of 4s floating around here. This is a trig integral. I know how to do this. Whew. It's part about line integrals. Everything becomes a one variable integral. All my tricks from chapter 7 get to get used. I know how to do this. Although I will admit, 4 to the 4th, and another 4. So I've got 4 to the 6th. So I'm going to stick a 4 to the 6th out in front here and just do the integral the easy way. Sure. 4 to the 6th integral minus pi over 2 to pi over 2 cosine t sine to the 4th t dt, right? So if I let u be sine of t, then du is cosine t dt. So that's going to be u to the 4th du. Wait a minute. I need to do one other thing. I need to change the limits. What is cosine of negative pi over 2? I'm sorry, sine of negative pi over 2. Cosine of, sorry, sine of pi over 2. It's scary. Nope. You said nice and easy polynomial. $64, $256, $1024, 4,096 times whatever the result of this integral is. So again, I don't know what this vector field, what this function x, y to the 4th looks like. But it's going to get pretty big as y gets bigger, right? So if I think about this, as we go along this circle, we're going a long way, right? Y to the 4th. y to the fourth is gonna be a really positive big number, isn't it? So we've got a lot of area under this curve as we go around this circle. We start out very high up, y to the fourth, because we start down here where y is -4. And we move that way, and y gets bigger. So we go down and then back up. Oh, wait, we also have to multiply by x, don't we? So x is 0, then x gets bigger. So we're gonna go, well, hey, we're gonna look like this thing. Well, instead of being a quarter circle, it's gonna be a semicircle, not a quarter circle. And the area under that fence is whatever number we come up with here. For a question. Because the integral from -1 to 1 of u to the fifth over 5 is 2/5. 2/5 times 4,096 is 8192 over 5. This is what happens when you practice times 2 powers of 2 all the damn time. Yes, ma'am.
Could you sum up 16.40?
40. Which 40 itself?
Yes.
40. 40 says, find the work done. Wait a minute. Find the work done. Work done. Integral f dot dr. Work done. I know I'm doing work. I know I'm doing this integral. Force field x squared I y e to the x. F x squared I y e to the x j on the curved particle that moves along a parabola. I really am very happy they gave me an equation explicitly this time. So the problem is coming up with R of t, right? I've got F, I just need R of t. Start at the point 1, 0. I move to the point 2, 1 along this curve, which is x equals y squared plus 1. How do I do that parametrically? But I don't have the line, right? That would give me this path. I gotta go along the curve. It's not a straight line. This, until I know something about this equation, I can't change the path. And we don't know what the thing is I need to know, and we'll figure that out when we get back. But it would be nice if I could switch paths, but I don't know if I can switch paths here. I have an advantage. I can think of this graph as a function of y, right? So what if I were to make my parametric equations? Well, y is just t. Then what's x? Oh, it's my function of y. And wait a minute, if my parameter is y goes from where to where? You know how to do the rest of it, don't you? I take the x and the y, I put them in the equation, I put the dr. There's r of t, dx, dy. Look at all the we got to remember how to do, people. We did parametric equations back in chapter 10. Technically, we did them in pre-calc if you took that here. Now, so I've got to remember how to do the parametric equation. I've got to remember how to do a dot product. That was in chapter 12. I got to remember how to do the derivatives because that was what we were doing to get dr. I got to take dx, dt, and dy, dt. And then I have to do the dot product, and then I have to do an integral. There's a reason we're on chapter 16, people. It took a long time to get here. Better, Nora? Yeah. Second order differential equations. Oh, no. It's chapter 16. Sorry, chapter 17 is the very second topic in there. We're going to revise chapter 9, and then we're going to do chapter 17, and then we're going to take it and move further. DiffyQ is fun. DiffyQ is real. It's real life. I would love to tell you it's not, but the way we get all the models that we're doing, the way we get things to work in the real world is to set these sorts of differential equations up. They're the models we do for everything. Matter of fact, I just got, where did I put those? I just got modeling equations. The Society for Modeling with Differential Equations actually put out a textbook. And I was debating whether or not to use it next semester, but they have projects. And here's one of my favorites. A system of first order linear differential equations to model LSD absorption in the body. With real data. You give them the drug, you wait a certain amount of time, and you measure the amount of drug in their body. How effective is the human body in getting rid of this drug? This is what pharmacokinetics is all about. This is the way doctors look at metabolism of drug mechanisms around the globe. Here's a new medication. How effective is it at doing this thing? Now I set up a differential equation based on this data. I do numerical modeling, and I go, oh, what curves fit here? I have an equation. I learn from it. If I take away the fact that this is done with LSD and I do it with alcohol instead, this is where the state and the federal government figured out how long it takes to metabolize a standard drink. So if you have a drink, whatever that drink is, a 12-ounce beer, a 5 1/3 ounce glass of wine, or a 1 1/4 ounce shot of 80 proof alcohol. I wish I was making this up. That's a standard unit. If you have 1 unit of alcohol, how long does it take your body to recover from that? I got to measure your blood alcohol concentration over the course of time. I can do that by measuring the amount of alcohol you exhale, because that's how you get rid of it. You metabolize it by converting it to CO2 and breathing it out, and metabolizing it to other water and excreting them. But you've got to get it out of your body. How do I measure that? I can take blood samples, or I can take a breathalyzer test. And I can use that to approximate your blood alcohol concentration. Then I can figure out, on average, it takes a person an hour to fully metabolize a drink. But then I can set things like blood alcohol level concentrations. So that's what DiffEq does. It does all the modeling to get the equations to figure stuff out. One of the examples I do in class is part of the thermo course. It's on metabolism of potassium. Because potassium comes in a radioactive isotope. And if you eat potassium and it's radioactive, how long does it take to decay out of your body? Where do you eat potassium? Bananas. So the easiest way to hide radioactive material is to hide them in trucks full of bananas. That was actually a plot point in a spy novel written by Tom Clancy. Useless crap. But iodine breaks down into calcium, potassium breaks down into calcium and iodine and two other ion components. Well, how does it break down? And the three chemists sitting in my DiffEq class were really pissed off when they walked into thermo and they sat down and they said, this is exactly the problem Sassmore did 3 weeks ago. And I was observing class that day and I opened up the DiffEq book and I went, yep. And Dr. Miller went, really? You did the whole thing? We're going to do a lot more of that on the computer this year than doing it all by hand. I learned so much about those tricks. All right, ask me more questions before I wander off in a different direction again. No? Advantage 1, the next time I see you is a week from today. Disadvantage 1, the next time I see you is a week from today, and that's when this is due. So if you put it off, it will leak out of your brain between now and then. Please get this done so you can enjoy your break. Have a wonderful Easter. I will see you all in a week. And on Wednesday, when we get back, Nora, I'll figure out whether or not I'm actually allowed to change paths. Because it'd be so much nicer to use the straight line. When can I change paths to make my life easier? That's next week.